This is Mrs. Rainbow, and I am going to be talking to you today about oxidation reduction reactions. This is like my fifth time making this video. I really hate oxidation reduction reactions. I got my candle burning, the light just went out, but my candle's burning. I think we're going to get it right this time, and I am going to love oxidation reduction reactions after this. So typically, I don't teach this just because I don't know. I just think it's tedious, but it's probably good for you to know. It is interesting in the fact that it's basically what batteries are made up of, and it's your biological reactions, such as photosynthesis and cellular respiration, or oxidation reduction reactions. So I should be more open-minded. I just find it tedious, and I tend to make a lot of mistakes on this. So now I see why the videos have mistakes on them too. But we're gonna do it. So let us begin, ladies and gentlemen. Yes. What is an oxidation reduction reaction? That's the first question. I'm sure you're all dying to know. So this is a chemical reaction that has a transfer of electrons. So the first thing just to say here is that we have the 5 types of reactions, which we talked about in the last video. Those stand. You always have those 5 types of reactions. Some of those reactions, not only are they what they are, they can also be a redox reaction. And redox is the word that we use for oxidation reduction reaction. So this is where we have a transfer of electrons. And this picture shows it actually really nicely. You see you have an element here that has an electron, and it's so nice it gives it to this element right here. And so we say that the one that is giving the electron is the oxidation part of the reaction, and the one that's gaining the electron at the end is the redox, or the reduction part of the reaction. Okay. Now, in this is the good stuff, is that you have 2 types of chemical reactions that are always redox: simple replacement and combustion. Both of these are always a redox reaction. So if you have those, you can already know that not only is it just simple or single replacement, it's also redox. Double replacement is never a redox reaction. So that's something you can also know, is whenever you have a double replacement reaction, it is not a redox reaction. So that's just some helpful tips, and that actually will help you with 4.06. So what do the terms oxidation and reduction mean? Well, oxidation means that an element loses its electrons. So you have this picture here. This guy is the oxidation part, because what's happening is he has the electron and then he gives it away in the products. So this is the reactants and the products. In the reactants, he has the electron, and the products, he gives it away. So that is the oxidation part of the reaction. If there's an oxidation part, there's going to be a reduction part. So if somebody loses the electrons, that means somebody's going to gain the electrons. And that's this part right here. This guy needs an electron. And so the reduction part of it is he gains the electron. Now this probably sounds very familiar to you, because this is how we create ionic compounds. Ionic compounds are where you have one element that's losing its electrons, and then you have another element that's gaining those electrons, the cation and the anion. So when you have that, you definitely have a redox reaction going on. But there's other ones that don't look like that are also redox, which is the annoying part of it. I was like, oh, it's just ionic and covalent. And I'm like, oh, no, it's not. All right, so I like this because it's Leonardo DiCaprio. This once again shows my age. You probably don't even like this guy. You're like old fart. But for me, he's like super dreamy. Titanic. Oh my God, loved him. So, and then in the other movie, how about them apples? What was that movie called with Robin Williams? I forgot the name. And Ben Affleck was in it. Okay, I don't remember. But anyway, you get the point. So this is a nice way to remember the difference between oxidation and reduction. And so in an oxidation reaction, so it says Leo says grr. And that's what Leo's saying. Look, he's saying grr. And so Leo stands for loss of electrons is oxidation, and grr stands for gain of electrons is reduction. So loss of electrons is oxidation, gain of electrons is reduction. So this is just a cute, funny way to remember it. And honestly, it is the way I remember it. And looking at Leonardo DiCaprio is not bad. I mean, he's old, but you know, so am I. All right, so let's show you what a redox reaction looks like. So this is very simplified. It'll get a little bit more as we go along. But this is, if you notice, I've just put the reactants in here because I want to practice with you predicting products, balancing, and then we'll look at the redox part of it. So it says solid sodium. So you would write sodium, and it's solid, so you'd write the little S there. Reacts with means plus. Chlorine gas, chlorine. All by myself, half sprinkle it, and chlorine is right there. Half sprinkle it. So that means when it's all by itself, it's Cl2. And then we put a little gas behind it. Now, we want to predict the products. And when we predict the products, you have A plus B. These are two elements. And when you have two elements in the reactants, that means you're going to get one product in the one compound in the product. So now let's look at what it's going to be. You've got sodium, which is +1, and you have chlorine, which is -1. So those charges, we just take the numbers and crisscross them, and you get sodium chloride. We are not done yet, okay? So we have now written the reaction, but now we have to balance it. So let's balance it. Yay! So when we balance it, you have sodium on this side, and it has 1. Okay. And then you have sodium on this side, and it is also 1. Then you have chlorine on this side, which is 2. And you have chlorine on this side, which is 1. So we want to balance the chemical reaction. My kids are home. We want to balance the chemical reaction. And so we want to put a 2 here. We put a 2 here. That's 2 sodium, 2 chlorine. We're almost balanced. If we put a 2 here at the sodium, that gives me 2. And now we are balanced. So we've done all of that. I made you go through all of that because I'm making you work for your money. You worked hard for your money. Now what we're going to do is we are going to redox this. So how do we look at this in terms of a redox oxidation reduction reaction? Okay, so you look at sodium, and when you have an element by itself like that, the charge of that element is 0. It's 0. There's no charge there. The charge of this element, chlorine, is 0. Now the charge of sodium and chlorine together make up 0. But if you remember, we said sodium was +1 and we said chlorine was -1. So now we look at this and we see that sodium goes from 0 in the reactants to +1 in the products. So +1 in the products. So what that means is that it lost an electron. Leo goes grr, losing electrons, oxidation. So that means this is the oxidation part of it. And then the second part of it, there's got to be a reduction. So it's going to be Captain Obvious, but we're going to write it down anyway. Chlorine is 0 in the reactants, and if you notice, it goes to -1 in the products. Grr, gaining electrons, reduction. So this is the reduction part of it. Okay? That's it. So you're like, that's a lot. So if you see ionic compounds, as long as it's not double replacement. So if it's single replacement and combustion, it's totally going to be a redox also. In terms of decomposition and synthesis, if you see an ionic compound in there, then it's probably going to be a redox reaction. Okay, so that's how it goes. Now, the thing is that there are some reactions that are not that clear. So obviously with the ionic compounds, it makes sense because you have your cation and your anion. But you also have some reactions that don't make sense, that they're covalent compounds, but they can also be redox. And this is what we do when we talk about combustion. That's one example. So when we look at combustion reactions, or when we look at any reaction that has covalent compounds in it, how do you determine the charge of something that has a covalent compound in it? Well, you look at the electronegativity. And if you remember, electronegativity is like how attractive an element is to electrons. Like, there are certain elements out there that electrons are like, oh my God, you're so hot, I want to be around you. And the most attractive, good looking element is fluorine. Fluorine is super hot. All the electrons want to be around fluorine. And it's because of where it is located in the periodic table. This goes back to Module 2. Module 2, DBA. Remember I asked you about electronegativity in that. Because it has 7 valence electrons, it only needs one more, so it's very attractive. The one that's the least attractive, so this one is like super hot. The one that's least attractive is francium. Wah, wah. Nobody likes francium. Ugh. Because francium has only one valence electron, and it's like all the way out in like the 7th shell, so like no electrons are attracted to francium. And then you have everything in between. So if you don't remember electronegativity and periodic trends with electronegativity, go back to Module 2, 2.07, and just kind of refresh your memory on how to determine electronegativity on the periodic table. Or you can just get a periodic table that has the electronegativities on it. So what you're going to do is when you have a covalent compound and you want to figure out the or the oxidation reduction of it, the atom with the higher electronegativity has a stronger pull. So the more attractive elements like francium, electrons want to be around it. So they're kind of more, they pull the electrons around it more. So they tend to be more negative, which is reduced. The atoms that have a lower electronegativity, they have less of a pull, so they're positive, so they're considered the oxidized end. So that's how we assign or we look at oxidation numbers and like look at like redox reactions in terms of covalent bonds. I don't know how much will be about this on your test if you're a regular student, but it was mentioned in your lesson, and so I thought I should just kind of like put it out there. But honestly, this is really hard to understand if I don't talk about the next thing, which is not something that regular needs to understand. It's just what honors needs to understand. So that brings us to our next thing, and that is if you are a regular student, turn the video off now and go and get yourself some ice cream. Just shut it down because you don't need to know this. Unless you want to know it, if you want to be that person, which is cool, you can totally do that, but don't strain yourself, really. It's almost the end of the semester. You don't need to strain yourself. If you're honors, you have chosen to be a part of this world. So you are a part of our world. We going deeper, baby. We going deeper into redox reactions, so hang on tight because here we go. Regular people, turn it off now. All right. Hello, honors people. Thank you for being here and for wanting to continue your education. I wonder if I can get my light to go on now. Nope, it's still not going on. It's just really temperamental. Okay. So, welcome. Let's talk a little bit more about redox reactions. So what do we need to know? So in redox reactions, there are some reactions that you cannot figure out if it's a redox reaction just looking at it. And that's when we assign oxidation numbers. So we use this to determine if a reaction is a redox reaction. This is like the proof that it's a redox reaction. How it works is it provides a way for us to track electrons in the reactants and the products. So we look at the electrons in the reactants, we look at the electrons in the products, and we compare the change in the electrons. And if there's a change, it's a redox reaction. The oxidation number is imaginary. It's an imaginary charge, and it's basically what we're doing if we're like saying like, what if this is an ionic compound? Because sometimes they're covalent, and that's when you have to do that thing that we talked about in the last part with the regular peeps. Okay. So I don't really think I gave an example because I don't feel like doing it. If you want to see an example of that, we can try that maybe during live lesson. All right, so rules for assigning oxidation number. You need to write these rules down or make a picture of them, or I don't know. You need to have these rules when you're doing this because they're going to help you. And the first thing is that there are certain groups on the periodic table, because your periodic table is awesome, where you can just figure out the oxidation number just looking at where they are on the periodic table. The first is group 1. They are +1. And then group 2 is +2. Group 3 is not, only aluminum. So aluminum is always +3, but the rest of them are kind of wonky. Halogens are -1, That's group 7, by the way. Group 7 is halogens. I don't know why I wrote down the name for halogens, but not the other ones. But anyway, group 7 is halogens. The only time they're not -1 is when they're in a polyatomic ion. When you have an ion, the oxidation number for that ion is equal to its charge. So Al plus 3, that means that the charge for aluminum is plus 3. That's the oxidation number. Okay. If it's a polyatomic ion, then it will be the sum of the oxidation numbers will be equal to the charge of the polyatomic ion. So NO3 -1, the sum of nitrogen and oxygen 3 times must equal -1. Okay. So then the next one is elements, molecules, and compounds. Now these guys, they have an oxidation number that's basically equal to 0. So this is what we were talking about with the regular students, like sodium and chlorine. Both of these are just molecules. This is an element, this is a molecule. Their oxidation number is 0, okay? So there are more rules. So the next rule is hydrogen, and hydrogen is always +1. Oxygen is always -2, except when you find it in peroxides like H2O2, where it is -1. Hopefully you won't see that. I didn't see that, so hopefully you don't see that. When you're finding the oxidation number of 3 elements in a compound, save the middle one for last, because you'll see it'll make it easier. So these are the rules for assigning oxidation numbers. So now let's do a couple of practice problems with this, just to kind of show how this works, okay? All right, so here's where this is where I keep screwing up and having to repeat myself over and over and over again. So the first one is hydrochloric acid. So let's pray to all the gods out there that I get it right this time. So I don't know why, but I guess my math is off. So what you do is you write down the elements. You have hydrogen and chlorine. Chlorine is a halogen, okay, and it is found in group 7. So we can say what it is, that's -1. Hydrogen is +1. So this is really easy, and both of these equal 0. There's no charge on hydrochloric acid. So what that means is that this is equal to 0. So the hydrogen, let me erase that. The hydrogen is +1, and the chlorine is -1. That's the oxidation numbers for hydrogen and chlorine. Why are we doing this? We're doing this because when we get to a reaction, we're going to be doing oxidation numbers for all the parts of that reaction, and then we're going to be looking at the change in these oxidation numbers from reactants to products, and if there's a change, it's a redox reaction. So that's why we're doing this, because every time I do this, I'm like, why are we doing this? I have to remind myself that's why. We're assigning these oxidation numbers so we can figure out if it's a redox reaction. So these are just compounds here to show you how we assign oxidation numbers. And then I'll show you one example where we actually put it into a reaction. Okay, so that's the first one. So the second one is this really interesting compound here, AlNO3N3O9. So I'm going to list out the elements. I kind of like listing out the elements for it, okay? And then what I do is I put the charge of the ones that I know next to it. And if you remember that rule, that you do the middle one for last. So aluminum is always +3, and oxygen is always -2. Now you have to look to see what the subscripts are, because the subscripts play a role in this. So there's a 9 here, so you're going to multiply the oxygen by 9. And there is a 1 with the aluminum, so you're going to put that one there. Now, this one right here, nitrogen is one that you have to kind of calculate. You can't look at the periodic table. You can't figure it out. So for nitrogen, I'm going to put an X there. And if you notice, there's a 3, so it's going to be 3X. So all of these have to equal 0. This is a neutral compound. So now you are doing basic algebra where you are solving for X. So it's 3 plus 3X minus 18 equals 0. Okay? So what do? Okay, so I can take the 3 and the 18 and I can make this 3x minus 15 equals 0. Now I'm going to solve for x. I'm going to move the 15 to the other side, and then I divide it by 3, and that tells me that x is plus 5. And so that means that the charge on, I should have put this 3 this way. The charge on nitrogen is plus 5. I'm going to be honest with you, it's usually plus 5, just so you know. Like, I think there's a couple of instances where I've done this where it's not plus 5, but it seems to mostly be plus 5, just so you know that. So these are the charges. So aluminum is plus 3, nitrogen is plus 5, oxygen is negative 2. Okay? So there you have it. Oh, and I'll write them over here so you can, you don't need to see them. Okay, so that is figuring out oxidation numbers. Let's do another one. So the next one is super easy because if you notice, it's S8, so it's a molecule. So super easy, its charge is 0. Boom, done. Now let's do a hard one again. Let's do this one right here. So this one's different because it has a charge of negative 2. So you have chromium and you have oxygen. All right. And so you know that the charge of chromium is negative. I'm sorry. You know that the charge of oxygen is negative 2, and you have to multiply that by 7. We don't really know the charge of chromium because it's a transition metal. And we know that it's times 2. So these charges have to equal negative 2. So once again, we are going to be solving for x. So it's 2x minus 14 equals negative 2 in this one. So then we add the 14 and we add the 14 and you get 2x equals 12, okay? And so then you divide by 2, so x equals 6. So that means that the chromium is plus 6. So the chromium is plus 6, the oxygen is negative 2, and that's how we figure out this one, okay? That's the oxidation charges. All right, so moving right along. Let's do the last one. I really don't want to do the last one, but I'm doing so well. I haven't made any mistakes that I know of. If I do, text me. So you have this compound here. This is a neutral compound, okay? You have oxygen, which is negative 2. And this is this compound, this is an ionic compound, okay? And if we were to like look at this, it's iron sulfate, right? And iron sulfate, sulfate's negative 2, iron is plus 2. So it's telling you the charge is plus 2. So there's only one iron, there's 4 oxygen, and we don't know sulfur, okay? So what we do is we want to make this equal to 0. And so it'd be 2 plus x minus 8 equals 0. And then that negative 8 and then plus 2, so it's going to be x minus 6 equals 0. Then you add 6, So this sulfur is going to be plus 6. Okay? And I got it right. Hey, I think I did them all right. Yay! I get souped up on the math. Like, I don't know why even, because I love algebra. It's like my favorite thing on the face of this earth. But anyways, those are assigning the oxidation numbers. Woo! So now we have assigned the oxidation numbers. Now let's figure out how do we use these oxidation numbers to determine if a reaction is a redox. Are you ready? You might want to take a break and breathe for a second after that, because actually that was quite painful. So, and I'm sorry, at least I acknowledge that it's painful, right? At least I'm real. So here's what you do with a reaction. So with a reaction, if you want to figure out if it's a redox reaction, the first thing you do is you assign oxidation numbers to all the elements in the reaction, okay? If the oxidation number of the element changes from the reactant side to the product side, it's redox. Then you remember that Leo says Gur. Losing electrons, oxidation. Gaining electrons, reduction. If you're gaining electrons, that means that you are getting more negative, which is reduced. If you're losing electrons, you're becoming more positive, which is oxidized. Now, this is the last part, and this is really annoying. And that is they also want you to recognize the reducing agent and the oxidizing agent. This is only in the reactants. And basically the substance that is oxidized is the reducing agent, and the substance that is reduced is the oxidizing agent. I know it sounds confusing. It is confusing. I'm going to show you an example, and you just keep coming back to it, and hopefully it will make sense to you. But I know this is confusing. I can feel it. I feel your confusion, and you're not even watching. I'm like not even seeing you do it right now. Okay, so we've got two examples of this, okay? Because I figured you need two examples because make your life more difficult than it already is. No, actually, but just to show you, okay? All right, so let's follow our rules. So the first thing is we're going to assign oxidation numbers. We're going to figure out if this is a redox reaction, okay? Which it is because, I mean, obviously, but let's say we didn't know. All right, so we look at this one. We have iron, okay? And this is just a simple element, so that means its charge is 0. We have oxygen, simple molecule, its charge is 0. Now we have iron 3 oxide. So this we have to figure out its oxidation numbers for. You have iron and you have oxygen, okay? Iron is -2 and there's 3 of them. I'm sorry, oxygen is -2 and you have 3 of them, okay? Iron, we're not really sure, although I do know what it is, but let's pretend like we don't know, and it's 2. There's 2 of them. These have to equal 0. So it's 2x minus 6 equals 0. So what do? We solve for x, okay? Divide by 2, x equals 3. So what this is telling me is that for iron 3 oxide, that the iron is plus 3 and the oxygen is -2, okay? All right, so now that we've done all that, now let's look to see, is this a redox reaction? And it would be a redox reaction if there's a change in the charge. So we look over here and we see here's iron, here it's 0, and then its charge changes to 3 over here. So this is a redox reaction. Now, since the iron is going from 0 to plus 3, Leo says Gur, losing electrons oxidize. They've lost electrons. It's getting more positive. This is the oxidized portion of the reaction. The oxygen portion of it, if you notice, goes from 0 to -2. So Gur gains electrons reduced. It gained 2 electrons, so this is the reduced portion of the reaction. Now here's where it gets annoying, but it's easy. It's actually not hard. It's just oxidized. It's just that it's kind of annoying. So iron is oxidized. Iron is oxidized and oxygen is reduced. Now, if we want to determine the reducing agent and the oxidizing agent, what we would say is we would say that iron is oxidized and it is the reducing agent. It's just the opposite of it. Okay? So iron is oxidized and it is the reducing agent. And that means that oxygen is reduced and it is the oxidizing agent. So it's just the opposite. That's just the way to remember it. And when we're talking about reduce and oxidize, we're saying this is the oxidizing agent and we're saying this is the reduced agent. All right, let's do one more just to kind of like give us more pain. Let's do a combustion one because these are kind of complicated. And don't you want to do complicated? Yeah, you're honors, right? This is what you do. This is what I do, yo, Rainbow. I do complicated. So let's look at this reaction. So we look at this is cellular respiration. This is what my body's doing right now. I eat sugar and I breathe in oxygen and I breathe out carbon dioxide and release water. I'm doing this all the time. In fact, I need to fuel my cellular respiration after this video and stuff my face with a bunch of brownies, which is what I'm going to do. So we have this element right here, glucose, and we have carbon, hydrogen, and oxygen. Okay, so oxygen we know is -2 and there's 6 of them. Okay, Hydrogen, we know, is +1, and there's 12 of them. Carbon, we're not really sure, and there's 6 of them. This is kind of different. Like the carbon should probably like be in the middle, right? But it's not. So anyway, we're going to solve this. And so you have 6. Ooh, let me put it over here so I have more room. You have 6x plus 12 minus 12. And this is a neutral compound, so it's equal to 0. So this basically is 6x equals 0. 6 divided by 6. X equals 0. I did something wrong. What did I do wrong? Oh, no, I did it right. That's right. Okay. So that means that the charge of carbon is 0. So I did it right. Ugh. Okay, so now you have oxygen. Molecule, so easy. Oxygen by itself is 0. Yay! Okay. Now we go back. So carbon dioxide. Carbon, we're not really sure of, and there's 1 of them. Oxygen, we know its charge. Its oxidation number is -2, and there's 2 of them. This is a neutral compound, so it has to equal 0. So it's X minus 4 equals 0. So that means X equals 4. So that means that the charge of carbon is +4. So now we have the charges of oxygen and carbon there. Last one, we have water, hydrogen, and oxygen. Oxygen is -2, and hydrogen is +1, and the times 2, that equals 0. We're solid there. We don't have to do any math on that one. So that is the charges, okay? All right, so now what we need to do is we need to look at everything and see where there's a change in the number of electrons, okay? So the first thing I'm going to do is I'm going to look at carbon. I start with carbon here, and I have 0 here, and I have 4 here. So that means that this is a redox reaction, okay? But let's look at everything else and just kind of see where we are with everything else. If you notice, the hydrogen is +1 here, and the hydrogen is +1 here. So those we don't care about. Good. Good riddance. The oxygen here is -2, and the oxygen here and here and here, these two cancel out. Does it matter which one cancels out? No. Okay, but we'll just say that one cancels out. But if you notice, I'm going to erase this one and put it in a different color, that you have these 2 oxygens here. This oxygen is 0, and then it goes to -2. Does it matter which one it is? I don't think so. But this shows you that it's a redox reaction. I'm kind of making that up as I go on that one. So if you look here, you'll see that you have carbon, and it's going from 0 to +4. So it's becoming more positive, okay? So losing electrons oxidized. So this is the oxidized part of the reaction. And then you can see that oxygen starts with 0, and then it goes to -2. So this is, or -4 actually, you could say. No, let's just say -2. What did I put there? I just made it, okay, we'll just say -2 for now. I don't know if that really matters in the big picture of all this. All you need to know is that because it gained electrons, it is reduced. Now, in talking about reducing agent and oxidizing agent, because carbon is oxidized, that means that this whole compound is the reducing agent. We don't say carbon, we say the whole compound is called the reducing agent. Because oxygen is reduced, we say that this is the oxidizing agent. Okay? And now we're done. This was a really long freaking video. We're done. That's it. I am going to go and stuff my face with brownies. I suggest you do the same. On Thursday, I'll do some practice problems with the first video and this video, just so you guys can see a couple more of them. It's very painful. I don't like oxidation reduction reactions. I still don't like them. But I hope we had fun. I hope you had fun, and have a great night.